Hello, welcome to 9-4. In this video, we are going to be solving context problems with logarithmic models, and we'll also be evaluating logarithmic expressions with a calculator. Okay, so we'll go ahead and start there. And here, logarithmic models can be used to represent many real-world situations. These models often use base 10 or base E logarithm, okay, and these are the two very important logarithms that we will be using going forward, and a calculator is often needed to evaluate the function model for the conditions in a problem. Okay, so when we're evaluating or approximating the value of logarithms with a scientific calculator, again, base 10 logarithm is what we call the common log, and this is what the common log looks like. It's just log of x. It's kind of like the invisible base. Okay, so anytime you just see log of x, it's a base 10 logarithm. Now, the other type of logarithm that we use and that appears a lot in real-world context applications is base E. We call this the natural logarithm, and it is abbreviated as ln of x. Okay, so for example, if I was to calculate log 15, that is really log base 10 of 15. And if I was to calculate the natural log of 15, that is log base E of 15. Okay, so both of these can be evaluated in a calculator, and it's very important to differentiate between these two functions because the log of 15 is different from the natural log of 15. Okay, and in order to use these, we'll use the log key for common log, and we'll use the ln key for a natural log. Very straightforward, right? So let's go ahead and use our scientific calculators to approximate each logarithm, verify each result by evaluating the appropriate exponential expression, round all answers to 3 decimal places. So what we're going to do is we're going to go ahead and plug these in to our calculators, okay? So log of 13. Well, it's important to note that this is log base 10 of 13. Okay, and you will go ahead and find this on your calculator. Now, I'm going to be using a TI Inspire, which is different from what you have, but to access your common log and your log, it kind of looks the same. If you look over here, you'll see e to the power of x, and you'll see 10 to the power of x. Well, again, remember, logarithms and exponentials are inverses, so to access the inverse, all we're going to hit is the second button. So on your calculator, will be a second. On a TI Inspire, it's a control, and I'm going to punch in log. Now, oh, I got to go ahead and, I guess, open up a calculator first. Okay, so control, log. Now with a TI Inspire, you're able to punch in a base, so a TI Inspire can actually evaluate logarithms with different types of bases. If you just have a regular scientific calculator, it will automatically be log base 10. Okay, and we are evaluating, I believe it was 13. So I punch in 13, and we get this value, okay? And we want 3 decimal places or more, so 1.114. 1.114. Okay, now if I want to go ahead and verify this, because that's what the problem asks us to do, with an exponential expression, we're just going to go ahead and rewrite this. This is 10 to the power of 1.114, and we want to see, is this approximately 13? So I'll go back to my calculator, and I'll punch in 10 to the power of 1.114, and we get 13.002. So approximately 13.002. So this is verified. All right, now we're asked to go ahead and evaluate the natural log of 13. Okay, so the natural log of 13, sorry, I want to write this here, 114, is log base E of 13. Okay, but in our calculator, again, this is going to be the natural log of 13. So go back to the calculator. I will hit the control, or in your case, the second button, and I'll hit e to the power of x, which activates the natural log function, natural log of 13. I hit enter, and we get 2.565. 2.565. So approximately 2.565. Okay, and we want to go ahead and verify, is this as an exponential, so base e raised to the power of 2.565, is this approximately 13? So we'll check. E to the power of 565, there we go. It is approximately 13. Okay, so that is accurate, which we would expect it to be, right? Okay, so 2.565. All right. Okay, I'm going to go ahead. I'm going to stop the video here. The next video will focus on applying what we just did here to context problems, and then also looking at some context and evaluating the domain and the range with relation to logarithms. Okay, catch you next time. Peace. Hello, welcome back to this video. This is 9-4, and we are talking context problems with logarithmic models. In the last video, we were evaluating logarithms with a calculator. I forgot to give you guys the practice problems. Here is a couple of the practice problems. I would like you to just try these two, round to 3 digits or more, and then I'll post the answers right now. Okay, so I'll assume you have tried these. Here is the solutions. Okay, we're going to be utilizing this when we look at some context problems here in a second. All right, so here's our first context problem, and it says a biologist studied a population of foxes in a forest preserve over a period of time. From the data collected, the biologist created a model. T equals 8.85 natural logarithm of p divided by 62 to predict the amount of time in years it will take for the population of foxes to reach a certain number. So we're asked, describe the domain and the range of the function and include restrictions. So what I'm going to go ahead and do is I'm going to go back through and I'm going to kind of annotate the context to help me kind of understand what's going on. So we're given a function, and this is always important, right, in math. So here's our function, and we're told that the model is t equals 8.85 times the natural log of p over 62. So it's important to note, right, that p here, this is your independent variable, which means that this will be your domain. Okay, now what is p? Well, p, actually I'm going to write domain here. P is the population. Population of what? It's the fox population. Okay, so there's our domain, and I can write that here. So I'll write domain is the population of foxes. Okay, and they want us to also include restrictions. We'll talk about that in a second. I want to go ahead and go back to our context, and I want to talk about the range. So in our model here, t is our output. Well, this is our dependent variable. Dependent variable with the e. Okay, that means that this is going to be our range. This is our output. Okay, and what does t stand for? Well, this is used to predict the amount of time in years. Okay, so our range is time in years. Okay, and then now we'll talk about restrictions. So restrictions, I'm going to start out with the range because contextually this makes this is very, very intuitive to think about. Time, right, is always non-negative. We can't go back in time. So if I start measuring something, right, time, the initial value would be 0. Okay, and then it's always going to be positive. So time in years, where time is non-negative. Okay, now domain the restrictions is a little bit more tricky to think about. It's values that you're plugging into your argument of a logarithm. Now you need to think about a logarithmic function, and what I want to point out about a logarithm, in our last lesson we talked about the domain. The domain has to be greater than 0. Well, if you remember what a function of a logarithm looks like, okay, and actually I'll go here to my calculator to highlight this. Go to graphs. I'll just punch in the natural log of x. Okay, so you think about this. So domain must be, the argument must be greater than or 0, but the outputs are 0 at this value of 1. So my argument must be 1, right, in order to get time that is non-negative, right, or 0 or greater. So I want my argument to be equal to 1. Okay, so we have to think about this. What value of p will produce an argument of 1? Well, that's got to be 62, right? 62 over 62 is 1. Now, if my numerator increases, right, that will still give me values bigger than 1, okay, which is what I want. I want my argument, right, here, I want all these values to be bigger than 1. So I'm going to say population of foxes where the population is greater than or equal to 62. Okay, and if you think about this too, I mean, we can go ahead and kind of test this. You can test values if you're unsure. Like if I went to my calculator here and I punched in 8.85 times the natural log of, I don't know, let's say 30 foxes divided by 62. Okay, and notice how I get a negative time. That would be negative 6 years, okay? So again, if we go ahead and alter this, I can try something like 70. Okay, and I get 1 year. So it'll take about 1 year to get the population to 70. Okay, so part B, it says estimate how long will it take in years and months for the fox population to reach 1,000. Okay, so I want the fox population to be 1,000. Well, that tells me that P is equal to 1,000. Okay, and we want to solve for time. Okay, in years and months. So I know T, which is equal to 8.85 times the natural log of P, which in this case is 1,000, divided by 62. Okay, and this is going to give us T is equal to, so let's go ahead and plug this in. So here's my function, and I'm going to make my input 1,000. I want the population of the foxes to be 1,000. 24.6085. So 24. Oh, that's a terrible approximate. T is approximately 24. Now I forgot. 6085. Okay, so note that this is 24 years. So 24 years. This is years. And this is also years. Okay, but I want this portion to be months. So what I'm going to go ahead and do is I'm going to subtract 24, and I'm just going to convert, right? So I'm going to take 0.6085, and I'm going to multiply, did I say 24? I felt like I just said 24, by 12 months. I want this to be 12 months. Okay, divided by 1 year, right? This is conversion. Okay, so not there. Here we go. Okay, so I'm gonna have 0.6085 times 12. We get about 7.302. So that's 7 months. Okay. Whoa. All right. So let's go ahead and write our conclusion. So we can say the fox population will reach 1,000 after about 24 years and 7.302 months. 7.302 months. That seems like a obscure way to tell time, and I agree. But they say round to 3 decimal places, right? So you got to do what the problem asks. Okay, so that is the first example. I know these problems are kind of long, but the restrictions are kind of tricky, and we need to think about these. So what I would like you to do, here is a practice problem. Please pause the video. I want you to try this practice problem, and then I'm going to post the solutions. Okay, so hopefully you have tried this. Here is the solutions. The domain is the population of bacteria greater than or equal to 3,500, right? The population must be that, so that the range time is greater than 0. And then the calculation problem, it will take about 10 hours and 57 minutes for the bacteria population to reach that rate. Okay, I'm going to go ahead. I'm going to stop this video. I will make another video with example 2 and a second practice problem. Catch you next time. Peace. Hello, welcome back to 9-4. We're talking context problems with logarithmic models, and this is the second part. We're going to cover another example and then another practice problem. Okay, so here you go. The acidity level, or pH, of a liquid ranges from 0 to 14 and is given by the formula pH equals log of 1 over H plus, where H plus is the concentration in moles per liter of hydrogen ions in the liquid. Describe the domain and the range of the function, include restrictions. So let's go back in and let's highlight our function here. pH is equal to log of 1 over H plus. And we need to identify the domain. What's our input? What are we plugging values in? So here, H plus, this is our independent variable. And that's going to serve as our domain, okay? So I'll say here, the domain is the concentration of hydrogen ions in the liquid. Okay, and I'll put in parentheses, this is H plus. Okay, and it is comma in moles per liter. Those are the units. Moles per liter. Okay, so again, before we get to restrictions, I want to go ahead and go back to my formula. So here I have pH. This is the output. This is the dependent variable. Dependent variable. Okay, so this is our range, pH. And pH is the acidity level. So we can say the range is the acidity level of a liquid. Sorry, man, I'm sick. My throat. Acidity level of a liquid, and this is pH, the pH level. And the restrictions, right? The restrictions, they tell us here from 0 to 14. From 0 to 14. Okay, so there's your range with the restrictions. I know that pH, right? If you remember back to chemistry last year, pH is ranging from 0 to 14. So that being said, what is the domain of the function? Well, if we look at our formula up here, notice that our independent variable is in the denominator. So remember, a logarithm is 1. It has an output of 0 at 1. So we can ask ourselves, okay, what would make this argument 1? Well, if my denominator is 1, then my argument is 1, right? 1 divided by 1 gives us 1. So 1 will produce 0. Okay, so if I plug in 1, I get a pH of 0. Okay, well now how do I increase my output, right? It has to go to 14. Well, in the previous problem, notice our inputs, right, were in the numerator. Okay, and if you think about a fraction, right, the bigger I make the denominator, the bigger the output is going to be, right? So, vice versa. If I increase the denominator, the smaller the output is going to be, right? So, like for example, if I was to increase the denominator, what's 1 divided by 2? 0.5. What's 1 divided by 4? 0.25. What's 1 divided by 10? So you see, as we increase the denominator, our outputs get smaller, and that actually takes us below what we want, right, which is 1. So we're going to have to make the denominator smaller, right, to get a bigger output. Okay, so 1 is actually going to be our upper bound, and then our lower bound, okay, what value can h plus not be? Well, it can't be 0, right? So that's our restrictions. So 0 to 1 in moles per liter, where 0 is less than h plus, which is less than or equal to 1. Okay, and again, if you have a calculator, if you want to kind of test these out, we can go ahead and punch in log. Oh, it's not log. Log base 10 of 1 divided by, and we can make it something super small, like 0.1, and we get 1. Okay, so that just shows you that you're on the right track with your domain and range. Okay, so there's domain and range of this problem, right? And you really have to utilize your critical thinking here. These are not kind of very easy to calculate, so you have to do some thinking. All right, so part B, it says in a typical chlorinated swimming pool, the concentration of hydrogen ions ranges from 1.58 times 10 to the power of negative 8 moles per liter to 6.31 times 10 to the negative 8 moles per liter. What is the range for the pH of a typical swimming pool? So we're going to utilize our formula. pH is equal to log of 1 over, and we'll use our first value, so 1.58 times 10 to the power of negative 8. Okay, and this will be equal to, and we go ahead and just plug it into our calculator. I've kind of already pre-done that here, and we get 7.8, right? And our problem says round to the nearest tenth, so this is approximately 7.8. Okay, so I need to go ahead and I need to find the pH of the other endpoint. So log of 1 over, and here they say 6.31 times 10 to the negative 8th power. Okay, and this will be approximately 7.2 after we plug that into our calculator. If you're having trouble getting these values, a couple of things. One, make sure you're using the common log. You need to have a common log. And then secondly, if you're putting in 1 divided by these values, make sure your denominator is in parentheses. You have to kind of parenthesis off your denominator if you're using a TI-30, just a regular kind of like what my classroom calculators look like, okay? So this is 7.2, okay? So let's go ahead and write our conclusion, and we can say the range in pH for a typical swimming pool is from about 7.2 to 7.8. Okay, and there you have it. So here is a practice problem. Please go ahead, pause the video. I want you to try this, and then I'll show you the answers. Okay, so hopefully you have done parts A and B, and here is the solution. The domain is the intensity of the sound in watts per square meter, where the restrictions are greater than or equal to 10 to the negative 12 watts per square meter. Range is the intensity level of a sound in decibels, okay, where the intensity level is non-negative or greater than 0. So part B, what is the intensity level of a rock concert with a sound intensity of 3.2 watts per meter squared, and that would be about 125 decibels. All right, that is it for solving context problems involving logarithmic models. Catch you next time. Peace.